All right, let's start. I'm sharing the link to the problem. It's a hard. Hello, smart coder. How's it going? Minimum distance to type a word using 2 fingers. You have a keyboard layout as shown above in the XY plane, where each English letter, uppercase letter, is located at some coordinate. So here it is. It's a little dark, but hopefully you can see it. Hey Kantipur, how are you? For example, the letter A is located at coordinates 0, 0. The letter B is located at 0, 1, and so on. So these are the rows, these are the columns. Given the string word, return the minimum total distance to type such string using only 2 fingers. And we're told that the distance between coordinates is this, which you don't have to, but this is called the Manhattan distance. Is the absolute difference between each coordinate, adding them. And here there's a note that the initial positions of your fingers are considered free, so do not count towards your total distance. Also, your 2 fingers do not have to start at the first letter or the first 2 letters. Okay, so this is a different. Yes, I imagine that your fingers are free at the beginning. At any point, you could move them to 1 letter, and that has no distance. Just started LeetCode a few days ago. Lol, is Blind 75 a good list to start? Yeah, I think it is. I haven't done it myself, but it's a popular list. Depending on what your goal is, if you're preparing for an interview, I think it has a good mix of the kind of problems that are that occur frequently in interviews. By solving a lot of problems and liking it. Okay, so we have 2 examples, cake and happy. And well, the word is at most 300 characters and consists of uppercase English letters. So let's get our hands dirty just to get a feel for the problem. And let's try to solve the first example 1, which is cake. So we have this keyboard which has 6 columns, and let's only write the columns or the letters that we care about. So A, B, C, D, E. So yes, this is a wide column, but never mind. And K is here, right? Because A, B, C, D, E, F, G, H, I, J, K. Yeah. So these are the 4 letters that we care about in this example. And essentially, we need to partition the letters into 2 groups, one for 1 finger, and the other one for the other finger. And I think if you think about this intuitively, you should realize that they're kind of, you can cluster the letters into two clusters. So this is one cluster, and this is another cluster. And so that means that you can, why is it a cluster? Because these two are one unit apart, and these two are 2 units apart. So we can use one finger for CA at the beginning and the other finger for KE, and that's going to give us a distance of, so this is distance 2, this is distance 1, and we can do them independently. So the answer here is 3. And it seems to be optimal because you can't avoid, you can't do it in 2. You certainly can do it in 1, and I don't think you can do it in 2. And yes, if you look at the example, the answer is 3. But in any case, you don't need to be clever. I mean, we did this intuitively, but the first step, this is an optimization problem, because you are asked to find a minimum, an optimal, and there are potentially many solutions in the sense that you can make choices at each step. You choose either finger 1 or finger 2, and all those choices, you make all the choices for each of the letters in order, and in the end you have a value associated with the choices all the choices that you made. You want to find the minimum. That's an optimization problem. And even though with this example we try to be clever and we try to, instead of trying all the choices, we gave like an argument. Your first instinct when you get an optimization problem is to not be clever and to try to do, in some sense, brute force, try all the choices. And since I gave it away in the title of the stream or the video, you know we're going to be using dynamic programming, but let's pretend that we don't know that. At this point, we're just trying to go for the simplest solution, which is try all the possibilities. So now we need to, instead of trying it out, we want to predict if that's going to be fast enough. And so let's write down. So yeah, one observation that you can make is that whenever you are making choices, you make a choice for C of finger 1 or finger 2, you make a choice for A, then for C. And if you are at this point, you're at K, for example, you still need to make a choice for K and for E, but it really doesn't matter what you did previously. It doesn't matter all the combinations of finger 1 or finger 2. You only care about where your fingers are located at this point. And if you remember that, then you need to find an optimal way, given those positions, to finish typing the word. And that satisfied both conditions that you need to be able to solve this by dynamic programming. Notice that we observed that the subproblems will overlap because of what we said that doesn't matter what combinations of fingers you chose for all the previous subproblems. The current subproblem only depends on the positions at this point of the fingers. And the positions at that point are very few because you have, let's say that you have the letter that determines the position of the finger, and there are 26 letters, and even if you represent an extra position, which is that the finger is free, which is the initial state, you get 27 squared for finger 1 and finger 2. And this is a pretty small number. Whereas if you had to remember all the possibilities, then you would have an exponential number, right? Because for each letter you can choose finger 1, finger 2. So in this case, you would have 2 to the I if we're at the I position. And this is bad because this is exponential. So this means that the subproblems overlap. And then the other thing that we said is that for this subproblem, the subproblem where we are at K, we also want to minimize the distance. So that means that's what's called optimal substructure. Which means that the optimal solution to a subproblem consists of optimal solutions to the subproblems. Okay, so now it satisfies both conditions. Then let's characterize the subproblems. Let's say optimal substructure, I think. Yes, that's what I said. Substructure. Oh, I write it. Sorry. Structure. Okay, so let's say that we have D of I and I, which determines where we are in the word, and then we have the letter of finger 1 and the letter of finger 2. So let's write the formula. So if I is equal to n, where n is the number of characters in the length of the word, then the distance is 0. We finish typing, okay? However, if I is less than n, then, like we said, we have two choices, and we want the minimum of then. One is to choose finger 1, and in that case we need to add the distance. Let's say that we have a distance function from the position of finger 1 to the letter I of the word plus the distance from I plus 1, and f1 is not now going to be at this letter, and F2 doesn't change because we did not use it in this case. So that's one case, and the other case is similar. Is the distance. Hello, Goku. Hi. Distance from finger 2 again to word of I, and the distance from I plus 1 to well, here we don't use finger 1, so it stays in the same place, and here we add this. So yes, this is the formula. So now, to prove that this is going to be fast enough, let's count how many subproblems. Every subproblem just have two cases, and the distance we can calculate it in O of 1 in constant time. So every execution of this recurrence is going to take constant time. So we only need to count how many subproblems there are. And we know that I is in the range from 0 to 300 inclusive, and F1 is so it's a letter. It has well, the number of values of F1 is 27, like we said, and the same is for F of 2. So how many problems there are? I'm gonna teach you how to do these calculations. Maybe it sounds unnecessary because you can use a calculator, but I think it's useful to know how to deal with orders of magnitude to get a number sense for mathematical maturity, which the orders of magnitude just means that you count the digits or you use logarithms. So we need to calculate 3 times. Let's round. Yeah, guesstimation guesstimation is like a Fermi problem, where you also need to have some sense of the real world. And yeah, I think it's also useful for becoming better at engineering and software engineering. So anyways, we said it was 300. And then we have 27 squared. And now we're gonna do a trick, which is, so we know that we want to reduce this to powers of 10, okay? And you should know that, well, I guess that the square root of 10 is approximately 3. And the square root of 10, yeah, but it doesn't matter. The exact value doesn't matter. And the square root of 10 is the same as 10 to the 0.5. So that means that this becomes, and you add, when you multiply the numbers, the multiplications become additions. So this is 10 to the 2.5. 27 is pretty close to 30, which is this, and by the same reasoning, it's 10 to the 1.5, but this is squares, so it's 10 to the 3. So this is equal to 10 to the 5.5, which is small enough for the number of subproblems is pretty small. So of course you could do that with a calculator. We have here the So our estimation was around 300,000, and the exact number is this, which is close enough for our purposes. So I think we're ready to start coding this. So again, we're going to translate the equation into a recursive function, and we're going to use memoization to avoid recomputing overlapping subproblems. So let's call this mindist, and finger 1, finger 2. We said that if we typed all the entire world already, and then we want the distance between f1 and word I plus the mean distance of I plus 1, and here we moved our finger 1 to word of I, and f2 stays in the same place. And then the other one is pretty similar, so I'm going to copy paste it. Yeah, that's it. And here is finger 2 to word of I, and here finger 1 stays the same, and finger 2 goes to word of I. And initially we're going to use none for representing the finger, a free finger. And then we need to make sure that the distance between none and a character is 0. So here we want the min dist of 0, none, and none. So this is our main code. It's pretty simple. I would love to have this be one case only. Can I do that? I mean having a loop, but let's leave it at that for now. Okay, so we need to implement the this function, okay, that receives 2 letters, and we're gonna break it down. Why not? We're gonna break it down into many little and sweet helper functions. So one thing we need to change the representations, okay? These are characters. So one thing that we're gonna need is to get the index in the alphabet of a character, because we want to do calculations with numbers. So we want to turn the character into a number. So that is as easy as doing this in Python. Okay, so now we have that helper function. Then we want to change from 1 dimension into 2 dimensions, into coordinates on this keyboard. So let's write another helper that, given a 1D index, 1-dimensional index, it's going to give us. And notice that this only depends on the number of calls of the keyboard, which is 6. Let's keep it clean by this defining a constant, and this is going to be, the row is going to be determined by the division by the columns, and the column is going to be determined by the calls. Div mod. What do you mean by div mod? I mean, I am dividing and modding. Is there some kind of function like that in Python? Oh, let me check. Div mod. Python. So it returns a pair. Yes. Oh, I didn't know that. Cool. Thanks. So does that mean that I can do this or something like that? I don't know. Yeah, I know, but I like to use the libraries. Okay, so we got that. So we said that if any of them is none, we want to return 0, because that means that a finger, like one position, is free, so we can move anywhere freely. But then we want the zombie killer whale. Thank you for the follow. Welcome. So now we want to have point. So let's say that we have another function that gives us the Manhattan distance. So we want the chord of the index of A and the chord of the index of B, and we want the Manhattan distance. So that is all. And we're missing Manhattan of A and B, which is the absolute value of A of 0 minus B of 0 and A of 1 minus B of 1. Okay. So this should be it. Let's see if this works. Manhattan, I mistyped this. Yes, I did. Oh, thanks for the raid, Juice Meat. Thanks a lot. We are trying to solve this problem. I'm trying to explain all my thinking in as much detail as I can. So here, so I mistyped, had a typo. Let's see if now it compiles. Expected 2 arguments. Yeah, I don't think. So this needs 2 arguments. Oh yes, because I'm not passing. Yes, yes, obviously. So the coordinates of the index is div mod of I and calls. All right. Okay, so we pass the examples. Hey, Juice, thanks for the follow. Okay, so we pass the example. Let's try our luck. Is there any edge case that we need to take care of? So we're gonna have at least 2 letters. So if we have 2 letters, it's always 0, right? Because we can type each. So let's try one of those edge cases. Why not? So A and C. We need to get 0. And even if we have any combination of this, we're gonna keep one finger at A, one finger at C, and still it's gonna be 0. Easy. Okay, so let's submit. And we got it. Accepted. Easy, yeah. Well, Zombie, thanks for the recommendation. I really appreciate it. GG, good game, smart coder. I think the code is pretty simple. So I wanted to, does it matter which finger is which? Not really. So what if I do this? What if so let's say that the fingers are a what if the fingers are what? Yeah, no, this is not gonna be clean, I guess. Okay, let's see. So what if they are a tuple? And for in F, we want this here. So this is going to be this, and here I think it doesn't matter which one is which. So one, oh no, but I need to do this with indices, I guess. So I don't think this may be worse, but bear with me. So f of j, and here we want word, and f of 1 minus j, so that we get the other finger. Is this right? Seems so. Okay. Yeah, I don't know if that's better. Maybe the other one is clearer, I guess. By the way, let me share my solution. So notice, smart coder, that I broke it down to very simple functions, helper functions. Yeah, I think one heuristic to know when you can have a helper function is when they are very independent and general. Usually it's a tell that it's worth it. These are very common simple tasks. Of course, this is a very small program, so it's not a big deal, but this is useful for more industrial programming as well. So let me, did you understand why I used the mod for this? So we want to know, we wanted to transform from a 1D index into a 2D coordinate. and or 1D coordinate to a 2D coordinate. Yeah, I understood the mod part, but I needed to rewatch. I need to rewatch. Yeah, but let me just give you a way to think about it, like I did the other day with circles. Like, you can think about, so you are moving, the index is moving in one sense, it's moving from here and then to the second row and so on. So you can think about that as going round a circle of size 6 in this case. So this is 3. Whoa. 1, 2, and so on. So that means that the number of rows are going to be the number of complete turns that you do, and the column is given by the last turn, the one that is incomplete. So that's why when we have the coordinate, the index, we divide by 6 and we mod by 6. Notice that the number of rows does not matter, since I is always going to be at most 20, 25. So that's going to bound the row, and it's going to make sure that we are within the board. So yeah, that's why do you feel that you need to rewatch? Is there something? Let me talk about the takeaways. So we first identified, we first get our hands dirty by working out example 1, and we try to get fancy, and we try to skip to do as little, to be lazy and do as little work as possible. And we thought about clustering the letters into 2 groups and using 1 finger for each. And that's how we found that the minimum distance was 3. But then we stepped back and we said, hey, maybe we don't need to be clever. Maybe we can just try all possibilities with this technique called dynamic programming. So we started going down that path. We realized that dynamic programming was relevant because this is an optimization problem. We need to find a minimum. There are many choices that we can make at each step. When we make all the choices, we have a value associated with the potential solution, and we want an optimal, not the optimal. We want the value of an optimal solution. There could be more than one. And then we characterize the subproblems. We realized that we didn't need to remember all the choices that we made, whether we used finger 1 or finger 2 on each of the previous letters. Once we are at K in this example, we only care about where our fingers are at that point. And that gave us the clue that the number of subproblems overlapped, which is one of the conditions to use dynamic programming effectively. And then we also realized that there is optimal substructure, because when the subproblem where we are starting from K, for example, we also want to minimize. We want to minimize the rest of typing the rest of the word, the distance. So satisfy the two conditions. Then we wrote the recurrence relation in terms of a formula, which usually is simpler than writing the code. In this case, it's pretty similar, pretty much the same. And then we calculated how many subproblems there were so that we made sure that it was fast enough. We simplified the calculations to get it down to approximately a power of 10. We got 10 to the 5.5, which is very small. Usually, if you are in LeetCode, you never know, but if you are below 10 to the 7, 10 to the 6, you should be fine. We also realized that the execution of the function would constant time. So we convinced ourselves that it was fast enough, and we implemented with memoization the recurrence relation, and we assumed that we have this function, and then we broke down that function into very small helpers. We also represented this special state where fingers are free and getting to a letter is free. It doesn't add any distance. We represented with none, and we made sure that the distance in that case was 0. We did this translation between 1D coordinates to 2D coordinates in this board, which has 6 columns, and we had a Manhattan distance. So yes, that's all that we did. I think it was, maybe you learned a thing or two. So do you still feel that you need to rewatch it, Smart Coder? I mean, I'm not against it, but do you want me to explain something again? Or are you good? I'm good now. The summary is awesome. Okay. Yeah, I tried to do the takeaways so that you retain what we did, and maybe I can give a more high level overview so that it sticks. So that's all I have for now. It's been 45 minutes, so it's okay. So yeah, the title was provocative because I think this is a hard. It was classified as a hard, but I feel it should be a medium, to be honest. If you know dynamic programming, it's pretty straightforward, I think. Hey, Matthews, thanks for the follow. So yes, that's all I have for now. Thanks for watching. Thanks for the support. I'm still maintaining my streak of streaming every day, and I made it today as well. I want to keep it going. Sometimes I even streamed twice in the same day. I want to do another type. I'm doing only these kinds of explanations type streams that I prepare a little bit beforehand. But I want to also mix it up and maybe do some improvised solving, maybe answer problem requests. I'll probably be doing maybe a longer stream of that kind. So yes, thanks a lot, guys. See you later. Bye-bye.